Today we are going to speak about the IUPAC nomenclature for alkenes. First, we have to know what are alkenes. Alkenes are the unsaturated hydrocarbons that contain one double bond. The general formula for alkenes is CnH2n. This means that usually the number of the hydrogen atoms in the compound is double the number of the carbon. For example, if we have 5 carbons or benzene, okay, so the number of the hydrogens should be 10. If we have 6 carbons, the number of the hydrogen should be 12. If we have 7 carbons, the number of the hydrogen should be 14, and so on. The double bond in alkenes is also known as the olefinic bond or ethylenic bond. Those here on the right are examples of alkenes. So as we can see, all the alkenes in the examples have double bond, only one double bond. Now we are going to understand how we can give IUPAC name for the different alkenes. Of course, we can remember the rules of the IUPAC nomenclature from the part 1, video part 1, okay? And rules for nomenclature of alkenes are very similar. The only one difference is that in alkanes, we usually start the nomenclature by choosing the longest carbon chain. In alkenes, we should choose the longest carbon chain also, but this longest carbon chain should contain the double bond. Okay, so the first rule in nomenclature of alkenes is to choose or to select the longest carbon chain in the compounds, but it should contain the double bond. So we are going to select the longest carbon chain that contains the double bond. This longest carbon chain that contains a double bond will be the parent compound. We will put the name that is corresponding to the number of the carbons, and then we will put the ending in. For example, if we have the longest carbon chain in the compound is hexene, is hex, okay, so we will add the ending in, okay, instead of ane in case of alkanes. Then the alkyl groups attached to the longest carbon chain which contains a double bond will be indicated by numbers. Let's have examples so we will understand how to apply the IUPAC nomenclature naming rules. For example, if we have this compound, here we have the longest carbon chain contains 6 carbon, and as we can see, the longest carbon chain contains the double bond in here. Okay, so as we have 6 carbons, so we have hex, okay, and because we have one double bond here, this is alkene, so the ending here will be ene. Between hex and ene, we will put the number that indicates the number of the carbon atoms. We will put the number between hex and ene, we will put the number which indicates the number of the carbon that bears the double bond. Okay. Similarly here in this compound, in the second one here, we have the longest carbon chain. As you can see, this chain, okay, there is 6 carbons. In compound number 2, as we can see, we have the longest carbon chain, or the longest chain is the chain which contains 6 carbons. So the corresponding alkane is hex. So at carbon number 1, we will have ene. At carbon number 1, we will have ene. So basically, the mother compound is hex 1-ene. What else we have in the compound? We have here a methyl group. So this methyl group at carbon number 4, so we will write like this, 4-methyl hex 1-ene. Okay, let's go to the third compound or third example. In here, we have, in the third example, we have the longest carbon chain is that one, which contains 6 carbons. Okay, so the mother compound is hex. we have at carbon number 1 double bond. So we will write the mother compound as hex 1-ene. Do we have anything else in the compound? Yes. At carbon number 2 here we have a methyl group, and at carbon number 4 we have ethyl group. This is CH2 and this is CH3, so they are C2H5. This means this is ethyl group and this is methyl group. Okay, so we have 4, or we will write 4 ethyl, 2 methyl, and hex 1-ene. We use here, or we added, or we wrote the ethyl before the methyl, just before the E, alphabetically before the M. Here we have, as you can see, an alkene. This is an alkene because we have a hydrocarbon that contains 1 double bond. So basically, this is an alkene. If you would like to give this alkene a name according to the IUPAC system, so I'm going to apply the rules. First, I'm going to select the longest carbon chain that contains the double bond. So here, this blue chain is the longest carbon chain that contains a double bond. Then I'm going to count how many carbons I have. I have 1, 2, 3, 4, 5, and 6. So I have 6 carbons, so basically I have hex. Now I'm going to see, or to look, the double bond here at which carbon. Okay, at which carbon? Here the double bond is at carbon number 3. Okay, so I'm going to write 3. At carbon number 3 I have ene, means I have a double bond. At carbon number 3 I have ene, or I have a double bond. Okay, do I have anything else in the compound? Yes, I have a methyl group at carbon number 3. So I'm going to write 3 methyl hex 3-ene. As you can see, we have here trans. What is this trans? We are going to explain this a little bit later. Let's now focus on giving the compound an IUPAC name, and then we will explain how or what is trans this here, what is cis in here, and so on. Okay? Okay, so let's go to this second example. Here, if I would like to give this compound an IUPAC name, so I'm going to select the longest carbon chain. So to me, this blue chain is the longest carbon chain. If I'm going to count the number of carbons in this blue chain, there are 6 carbons. 1, 2, 3, 4, 5, 6. So basically I have hex. And at carbon number 3, 1, 2, 3. At carbon number 3, there is the double bond. So I have hex 3-ene. Do we have anything else attached to the longest carbon chain? Yes, we have a methyl group here. So I have here the methyl group at carbon number 3. I'm going to write 3 methyl hex 3-ene. Now, if you will concentrate or compare the two compounds in here that we have in here in this slide, you will find that they have the same name. We have here 3 methyl hex 3-ene, and here we have 3 methyl hex 3-ene also. But as you can see, the geometry of the two compounds is different. We have the compounds have the same name, same number of carbons, same number of hydrogens, but the geometry is different. In this case, we call those as they are geometrical isomers. So whenever we have two alkenes and they have the same name, or they have the same number of carbons, same number of hydrogen, and the difference is only in the geometry or in the arrangement or the order of the alkyl groups that are attached to the double bond, in this case we say that we have geometric isomerism, or it's also have other name which is cis-trans isomerism. Okay, let's go to more details about the geometric isomerism. What is the geometric isomerism? Geometric isomerism is a type of isomerism that arose in or arise in what is the geometric isomerism, or what are geometric isomers? Geometric isomers are isomers, okay, or similar compounds that in which the order or the geometry of the alkyl groups or the geometry of the two compounds are different. Geometrical isomers are alkenes that have the same number of carbons and same number of hydrogens, but the order or the arrangement of the alkyl groups or the branches around the two carbons is different. Let's see what are the two rules that based upon them I can decide whether the compounds are geometrical isomers or not. First, we have to know that to have geometrical isomers, we should have a restricted rotation. What does it mean by restricted rotation? It means to have double bond. Restricted rotation, it means to have double bond. Why we say that double bond means restricted rotation? Because if you look to those compounds which we have here, those are two alkanes. And those alkanes means that they have single bonds, not double bond. Usually in single bonds there is free rotation. This carbon freely rotates around the double bond, and also this carbon, so they are freely rotate around that single bond. They are freely rotate around the single bond. Okay, but whenever we have double bond, such as here, this free rotation is restricted or forbidden. It's not possible for this carbon or this carbon to rotate because we have now an extra pi bond over the sigma bond that prevent this free rotation of the carbons. So those groups around the carbons or around the double bond are restricted. They cannot change their location. They cannot move. They cannot change their places. They are fixed in their place. So this compound is not same as that one. This compound in alkane or in single bond, which contains single bond, is same as this compound. Okay, because they are changing, the groups are changing their location or their order all the time. They are rotating. This carbon is rotating all the time. So this can be down here at a specific moment. So both of those compounds are same. But when we have double bond, this rotation of this carbon or this carbon is restricted, and those compounds cannot be interconverted to each other. They cannot, there is no interconversion to each other. Those substitutions are fixed in their places. The rotation is restricted. So those two compounds are different. This one is different than the other one. In here, if we have the same groups, but the order is different or the arrangement is different, those are geometrical isomers. There is here a geometrical isomerism, okay? What is other condition? Let's see here. Here is an example. If we have single bond, compound that contains single bond, which is an alkane or a saturated hydrocarbon, the carbons here, they can rotate freely around this single bond, okay? They can rotate. So this group can change its place. It can be down there, and this can be come up, and so on. There is always a free rotation all the time, okay? But whenever we have double bond, as you can see in alkenes, usually one bond is sigma bond and the other is pi bond. Okay, this is the pi bond. As you can see, this pi bond prevent the free rotation of the carbons. So now those groups places are fixed. They are at this place. They cannot move or they cannot change their place. Otherwise, we would have to break this bond. Okay? So the presence of double bond or the presence of the bi bond prevent or restrict the free rotation, and this generate different or as a type of isomerism, which is called geometric isomerism. This means that whenever we have similar groups, as you can see, similar groups in two compounds, but the geometry of those groups or the order or the arrangement of those groups around the double bond is different. They are two isomers. They are not the same compound as we have in alkanes or whenever we have single bonds only. Okay, so let's now revise again when we will have geometric isomers, or how can I judge that I have geometric isomers in alkenes. We have two rules. To have a geometric isomers, we should apply two conditions should be applied. If you will find those 2 points in the alkene, this means that you have a geometrical isomerism and the two compounds you have are geometrical isomers. What are those two conditions? First, to have a restricted rotation. What restrict the rotation? The double bond. The double bond restrict the rotation around the axis of this. Okay, so whenever you have double bond, there is a possibility to have geometrical isomers. What else? What the other condition that we have to find so that we will have a geometric isomerism? One of them is not enough. We have to find both of them. The second thing is that we should find, or we should have, two different groups on the left hand end of the bond and two different groups on the right hand of the or right end of the bond. So this means that if I have two carbons, I should have two different groups at this carbon and two different groups at this carbon. It's not a problem if the groups are same, but at the same carbon I should have two different groups. Okay, so let's apply those two rules or two conditions to the following couple of alkenes so that we can decide whether they are a geometrical isomer to each other or not. Let's take the first couple of compounds. First, if I would like to see or to find out whether this one, compound number 1, is a geometrical isomer to compound number 2, I'm going to check those 2 points. If they are available in those two compounds, so they will be geometrical isomer to each other. Let's check. First, if they are geometrical isomers to each other, I should find that there is a restricted rotation around the axis of the compound. Restricted rotation means to have a double bond, so the bi bond of the double bond will prevent the free rotation, so the rotation is restricted. Here at compound number 1, yes, I have a double bond, so basically the rotation is restricted. At compound number 2, there is a double bond, so the rotation is restricted. So the first point is here. We can find that there is a restricted rotation. Okay, let's check the second part. The second part is that if I have two carbons here of the double bond, so the two carbons should have two different groups. So let's say that this is the right carbon and this is the left carbon, and here this is the right carbon and this is the left carbon. Let's check. For the right carbon at compound number 1, do we have two different groups? Yes. For the left carbon at compound number 1, do we have two different groups? No. Let's check the other one. For the right carbon at compound number 2, do we have two different groups? Yes. At the left carbon, do we have two different groups? No. So this second point is not applicable here at those. So those are not geometrical isomers. There is no geometrical isomerism in those two compounds. So this means actually that those compounds are same. They are same compound. they are same. If you can check, or if you will look, it's just they are same compound but from a different angle. Okay, if you are looking from here to this blue bond, you will find that the rest are the pink bonds, and same here from this blue atom, so the rest are the blue. So those are the same compound, they are same, they are identical. Okay, and no geometrical isomerism, they are not geometrical isomer for each other. Okay, let's check the second couple of alkenes here. Are they geometrical isomers to each other? Means, are they a compound that have the same carbon number of carbons and number of hydrogen, but the order of the groups around the double bonds are different? Let's check that. Let's apply the two rules we have. First, do we have a restricted rotation here? Yes, restricted rotation means that we have double bonds. Yes, we have double bonds. So there is restricted rotation. So those groups are fixed. They are fixed. Okay? Okay. Second, let's see the carbons at each side of the double bonds here. Do the carbons have two different groups? Let's check here if I have compound number 1 and compound number 2. In compound number 1, do the right carbon of the double bond have two different groups? Yes. Do the left carbon has two different groups? Yes. This group is pink and this group is green. So this means that might be methyl group and ethyl group. They're different. So yes. So now the two conditions are available here. Let's check the second one, compound number 2. For the right carbon, do this carbon have two different groups? Yes. Do the left carbon have two different groups? Yes. So here, those two compounds are geometrical isomers to each other. So they are geometrical isomers to each other. Okay? In geometrical isomerism, we say that one of them is cis and the other is trans. Okay, so whenever we have two geometrical isomers, we say that one of them is cis and the other is trans. Which cis and which is trans, we will discuss this later. Let's just focus now on finding out whether for each couple of alkenes are they geometrical isomers to each other or not. Okay, let's have those third couple. Let's check, let's apply the rule so that we can check whether there is geometrical isomerism in here or not. Okay, let's give this compound number 1, this compound number 2, and this right carbon and left carbon. Let's now apply those two rules. Do we have a restricted rotation? Yes, I have double bond in both compounds, so basically the rotation around the double bond will be restricted. Let's go to the second point. Do we have two different groups at each carbon? Yes, at the right carbon we have two different groups, and at the left carbon we have two different groups. Here on the other one, do we have two different groups? Yes. At the left carbon, do we have two different groups? Yes. So basically those are also geometrical isomers to each other. Let's check the fourth example here. Fourth couple of alkenes. Let's find out whether they are geometrical isomers to each other or not. Okay, so let's apply the first point. Do we have a restricted rotation? Yes, we have double bonds, so basically we have restricted rotation. Second point, this is carbon right and left, and this is compound 1 and this is compound 2. Let's check to the right carbon in compound 1. Okay, do we have two different groups at the right carbon of the double bond? Yes. Do we have two different groups at the left? Yes. In compound number 2, do we have two different groups at the right carbon? Yes. And at the left carbon? Yes. So basically those are also geometrical isomers to each other, or cis-trans isomers. Okay, so if you concentrate more, you will find out that this compound is the only one, or those couple are the only couple that don't have geometrical isomerism, and this is basically because we have 3 similar groups actually. Okay, but whenever we have different groups, as you can see, at least two, so there will be some geometrical isomerism. And if you get confused, just apply those two rules to decide whether the compounds are geometrical isomers or not. Okay, now let's go. Now we already know how to find out whether there is geometrical isomerism or not. Now we are going to the next step in which we would like to understand or to know which of the geometrical isomers would be cis isomer or which we will call it a trans isomer. Let's know the rule of the cis isomer and the trans isomer. When I can say that this is cis alkene and when I can say that, when can I say that this is trans alkene? First, let's check for this compound and start to apply the rule. When you would like to know whether the compound is cis or trans, just do a line, just draw a line that cut the double bond, that is perpendicular to the double bond. As you can see, it cut the double bond into two. Okay, and then give a number for this carbon or a symbol. This is the right one and this is the left one. Okay, then go to the right one and check the two groups that are attached to this carbon and select the one with the higher molecular weight. Which is the carbon of the higher molecular weight? Which is the group of the higher molecular weight here? Is it the methyl group in here or the hydrogen? If you will check the periodic table, you will find that the atomic weight of hydrogen is 1, while the molecular weight of methyl or methyl is 15, because the atomic weight of carbon is 12 and each hydrogen here equal 1, so we have basically 15. So the molecular weight of the methyl group is higher than the molecular weight of hydrogen. Okay, now put a symbol or a sign or asterisk at the carbon, at the group with the higher molecular weight. Go to the other side, to the left-hand carbon, okay, and check which of the two groups have the higher molecular weight. Of course, now we know that the methyl group is 15. The molar mass of the methyl group is 15, so now the methyl group is of the higher molecular weight. Okay, so first step in deciding whether the compound is cis or trans is to draw a line that cut the double bond into two. Then we go to the left hand, to the left, then we go to the carbon, the right carbon, and check which of the two groups has the higher molecular weight. And then put a symbol or sign at this group. Go to the left carbon and put a symbol also at the group with the higher molecular weight. Then let's now check the two groups of the higher molecular weight on both carbons. Are they at the same side of the double bond or at a different sides? So I have to draw an axis or a line like that, okay, and check whether the two groups of the high molecular weights, are they at the same side of the line or of the double bond or at different sides. So as we can see, both groups of the higher molecular weight are, as you can see, they are up. They are not down here, okay? They are above this line. So this compound is cis. This compound is cis. So if the two groups are in the same direction of the double bond, if the two groups of the higher molecular weight are at the same direction, the compound is said to be cis. Okay, let's go to the second one. But first we forgot to give a name. Of course, if I'm going to give a name, I'm going to choose the longest carbon chain. As you can see, this is the one with the longest carbon chain and it contains 4 carbons, so it's but. And at carbon number 2, there is the double bond, so it's but2-ene. Okay, now let's be back to the cis-trans or the cis-trans rules. Okay, I would like here to find out whether this compound is cis or trans isomer. So what I'm going to do is to draw a line that cut the double bond into two. Now we have a right carbon and a left carbon. For the right carbon, let's check which of the two groups will have the higher molecular weight. This methyl group, of course, have the higher molecular weight than the hydrogen. So let's put a sign or color or whatever we like. Now let's go to the left-hand carbon, left-hand end carbon here, okay, and check the two groups. Which of them have the higher molecular weight? Of course, this methyl group have a higher molecular weight than the hydrogen. So now those two groups with the high molecular weights, okay, are they at the same side of the double bond? Draw that axis. Are they at the same side, okay, of the double bond, or they are in different sides? This one is up here, okay, up, as you can see, it's above the axis, and this other one is below the axis, okay? So if they are at different directions, this compound is trans. So now let's summarize what we have learned until now. Now we know that alkenes are compounds which contains double bond. And second, in alkenes, we have some kind of isomerism that is called geometrical isomerism. Geometrical isomerism means that we might have two compounds. They are alkenes, they have same number of carbons, same number of hydrogens, but the order or the arrangement of the groups around the double bond or the carbons forming up the double bonds is different. In this case, a type of isomerism that is called geometrical isomerism arose. So how can I know that if I have a couple of alkenes, how can I know if those alkenes are geometrical isomers to each other or not? We said that we are going to apply this rule in which there should be some kind of restricted rotation and the two groups at each carbon should be different. Okay, next step, if we have or we are sure that we have two geometrical isomers, how can we decide whether those two geometrical isomers are cis or trans? We said the rule that first we have to cut the double bond or to draw an axis that cut the double bond into two, as you can see. Okay, and then we go to the right carbon and check which of the group attached to the right carbons have the higher molecular weight. Put a sign, put a color or anything. Then go to the carbon, the left-hand carbon, and check which of the two groups that's attached to the left carbon have the higher molecular weight. Put a sign, a color, or whatever you like. Okay, then compare the groups of the higher molecular weight on both carbons. Are they at the same side? So the compound will be cis isomer. If they are at different sides, so the compound will be trans. Let's go to further or extra examples. Okay, here we have another example. Check this one here. So now this alkene, this is an alkene, and if I'm going to give it a name, I should choose the longest carbon chain that contains the double bond. To my eyes, this is the longest carbon chain that contains the double bond. Basically, this is meth, eth, prop, bute, pent. So I have pent. And at carbon number 2, I should start the numbering from the carbon that is nearest to the double bond. Okay, so here at carbon number 2, I can find a double bond, so I have pent 2-ene. This is the mother compound. Do we have any other substitution? Yes, we have a methyl group here, as you can see. So at carbon number 3, this is 3 and this is 4 and this is 5. At carbon number 3, we have methyl group. So basically the compound is 3-methyl-pent-2-ene. Now, let's find out whether this compound is cis or trans isomer. Okay, so what I'm going to do is to draw a line that cut the double bond into two pieces. Now we go to the right carbon. Now we go to the right carbon and this is left carbon. So let's check on the right carbon. Which of the two groups attached to the right carbon have the higher molecular weight? Of course, here I have ethyl group, that one, and here methyl group. So this is lower. Okay, the one with the high molecular weight, we call that it's high priority. Okay, we don't always say high molecular weight, we say high priority. So this is the group with the high priority. Then we go to the carbon on the left and check which of the two groups have the high priority, or which is mean the higher molecular weight. Of course, we have here a methyl group that have a higher molecular weight than the hydrogen. So this is a group of the higher priority. Now we have to check the two groups of the higher priority, which is that one and that one. Are they at the same side of the double bond? Are they up to the double bond, above the double bond, or below the double bond? Both of them is at the same side. Both of them is up. Okay, is above the double bond. So this compound is cis. Okay, what is cis in the IUPAC? What is cis by the IUPAC rule? What is cis in the IUPAC rule? Cis, according to the IUPAC, is called Z. Z. Okay? Z. We write Z and put it between two brackets. So Z is similar to cis. Z is similar to cis. Let's go to the other compound. Here, the second one. We have here same name, 3-methylpentuene. But as you can see, the geometry or the arrangement of the groups are different. The arrangement of the groups around the double bond are different than that one. Let's find out whether this compound is cis or trans. So we are going to cut the double bond into two. We are going to draw a line to cut the double bond into two. Now we have carbon at the right and carbon at the left. For the carbon at the right, which of the two groups attached have the higher molecular weight? Of course, I have here ethyl. Here ethyl or ethyl group that is higher in molecular weight than the methyl. Okay, so we call or we say that this is the group of the high priority. Go to the left carbon and decide which of the groups attached to the left carbon have the higher molecular weight. We have here a methyl group that is higher in molecular weight than the hydrogen. We say that this is high priority. In a professional way, we say high priority. Okay, so now we should decide the two groups of the high priorities. Are they at the same side of the double bond or not? Let's draw this axis. Are the two groups at the same side? No, we have a methyl group that is above the axis and ethyl group that is below the axis. If they are at different sides, okay, so now I have a trans isomer. You can see here the two groups here were at the same side of the axis that I drew to through the double bond. Okay, but here the two groups are at two different directions. Okay, one is up and one is down here. So this is trans. What is trans by the IUPAC? We say it E. E. Okay, and actually E and Z are the first letters in the German words of right and left or something like that. I don't understand much German, but this is what I have read. Okay, so now whenever we have a cis isomer, we write it at Z or Z or Z, okay? And whenever we have trans isomer, we write it as E, okay? So we usually put Z or E if we are writing a perfect IUPAC naming. Of course, we can use cis or trans, but those are the most correct, okay? Let's go to more examples so that we will be much more familiar with the nomenclature of alkenes and the geometrical isomerism. Okay. Okay, now we have this compound. Let's give it a name and check whether it is a tet isomer or E or cis or trans. Okay, so first to give a name for a hydrocarbon, let's choose the longest carbon chain. And if we have here a double bond, so the longest carbon chain that contains the double bond. So we have here that. Okay, so what is the name of that? I have 4 carbons, so basically meth, eth, prop, bute. So I have bute and ene. But the ene or the double bond at which carbon? It's at carbon number 2. So I have bute to ene. Okay? Now let's find out whether this compound E or Z or cis or trans. So what I'm going to do first is to cut the double bond into 2 pieces. Okay, to draw a line that cut the double bond. And then we go to the right carbon and left carbon and check. For the right carbon, we have 2 different groups, which is the higher in molecular weight than the other. Of course, this one, the methyl group, is higher. Okay, put a sign, whatever you like, or write high priority. And this is because this is higher molecular weight than the hydrogen. Let's go to the left carbon in here, which have the higher priority or the higher molecular weight. Is it the hydrogen here or the methyl? Of course, the methyl. Molecular weight of methyl group is higher, so this is the high priority group. Now let's check whether the 2 high priorities group, are they at the same side of the double bond? This is the axis. Okay, are they at the same side? Are both of them above the double bond or below the double bond? One is above, as you can see, and one is below. So they are at different direction. So this compound is trans or E. Okay? Yes, here we have E bute to E. Let's go to the next example. Of course, we can see that it has the same name. It's same compound. If I'm going to choose the longest carbon chain like that, so it's basically it's bute 2E. But we have now to focus on finding out whether it's E or Z isomer. So I'm going to cut the double bond into 2, and then I'm going to check at the right carbon and left carbon, which at the right carbon, which of the 2 groups have of high priority. Of course, the methyl group is of high priority than the hydrogen. This means, or what we mean is that it has the higher molecular weight. So this is high priority than the hydrogen. Let's go to the left carbon. Which of them have the high priority? Is it hydrogen or the methyl? Of course, the methyl group have the high priority here for the left carbon because it have the higher molecular weight. High priority means of higher molecular weight. Okay, so now let's check the 2 higher priorities group or the 2 groups of the higher molecular weight. Are they at the same side of the double bond or at different sides? Of course, they are, both of them is above the axis which cut the double bond. So this compound, if they are at the same direction, this compound is cis, or we say that it is Z. Okay, cis, bute, Z, if we are writing a pure IUPAC name. Okay, so now we have Z, bute 2E. Okay, let's go to more examples. Here we have that compound. First, we should start to give it a name and then to find out whether it's a cis isomer or a trans isomer or E or Z. Okay? Okay. To give it an IUPAC name, we should choose the longest carbon chain that contains the double bond. So this is, to my eyes, this is the longest carbon chain that contains a double bond. Then we have meth, eth, prop, bute, pent. So we have pentene. Pentene. Here we have to mention the number at which the carbon atom or the double bond, the carbon atom at which the double bond is located. So we have here pentene. Next step, do we have any other substitution at the compound? Yes, we have a methyl group here at carbon number 3. So I have here 3-methyl pentene. Okay, third step is to find out whether there is Z or E compound or whether this compound is cis or trans. So what I'm going to do is to cut the double bond as you can see. into 2. Then I have the right carbon and I have the left carbon. Now check the right carbon, okay? The 2 attached group here, which one is of the high priority? Is it the methyl group or the hydrogen? High priority means of higher molecular weight. So of course this one, this methyl group is of high priority. Let's check the left-hand side carbon. Which of the 2 groups attached to it are of, which one has the higher molecular weight or the high priority? Of course, here I have ethyl group. And this is methyl, so this is of high priority. Now I have to compare the 2 high priorities group. Are they at the same side of the double bond? I drew this axis and check. Are they at the same side or different side? They are at different sides. This one is above the line, and this one, or the line that of the double bond, and this one is below. So they are at different sides. So basically I have a transisomer. Transisomer is E. Okay, so I have E, 3-methylpentene. Okay, let's go to the next example. Okay, and now in this compound, we have to put a name. So if you would like to have a name, it will be similar to the above one, to the above compound, because we have same exactly same chain of longest chain. The only difference is the arrangement or the position of the groups around the double bond. For example, in the first one, there was a methyl group here, down there, and the hydrogen is up there. But in this one, the opposite. The hydrogen is down there and the methyl group is up. So the 2 compounds are geometrical isomers, both of them. This one and this one are geometrical isomers. This one is E or trans, and this one is cis. Let's discover, or let's find out how it is a cis isomer. So we will apply the rules, which is first rule, which is to cut the double bond like this into 2 parts. Okay, this is the right carbon and this is the left carbon. On the right carbon we have 2 different groups. The methyl group is the one with the high priority, means the higher molecular weight than the hydrogen. So this is the group of the high priority. And then we go to the left side carbon. We have 2 groups. This ethyl group is the group of the high priority. The lower one, which is the methyl group, is of lower priority. This means that this one, which is the ethyl group, have the higher molecular weight than the methyl. Okay, now we have the 2 higher priorities group above the axis of the double bond, so they are at the same side. This means that this is the cis isomer or the Z isomer of 3-methylpentene, pentene, which is the cis. Okay, let's go to this compound. If we would like to give this compound a name, we will of course choose or select the longest carbon, the longest carbon chain, which contains a double bond. So this should be the one. And then we have meth-eth-prop-put-pent. So basically we have pent, and at carbon number 2, if this is 1, 2, 3, 4, 5. So at carbon number 2 we have the ene or the double bond. Do we have anything else attached to the carbon chain? Yes, we have a methyl group at carbon number 4 and another methyl group. So we have 4,4-dimethylpentene. Let's now find out whether this compound is a cis isomer or a trans isomer. Actually, we cannot decide that because the groups attached to the carbons of the double bond are not in a geometrical, are not drawn in a geometrical way. I mean, this should be like that. Should be drawn if I have a cis or a trans isomer, the groups should be drawn like this. Okay. For example, here is the hydrogen, and here is the rest of the compound, or the alkyl group of the rest of the compound. So we should have this shape. But if we have the whole or all the groups are not shown and are not branched, so I cannot decide whether this compound is a cis one or trans one. Okay? Okay, let's go to the next examples. We have that one. Okay, so this compound is basically, if I would like to give it a name, so I'm going to choose the longest carbon chain, which can be that one, for example. Okay, so now I have meth, eth, prop, but, and pent. So we have pent. And at carbon number 2, this is 1, 2, 3, 4, 5. At carbon number 2, I have ene, or a double bond. Do we have anything else? Yes. At carbon number 4, we have 4,4-dimethyl. So we have 4,4-dimethyl. So it looks exactly like the previous ones, or the previous, but of course, this is drawn, the compound here is drawn by or using the linear formula. We say about this formula when we use lines and the carbon atoms are just pointed as a head of a zigzag and the hydrogens are omitted. We say that this is a linear formula of drawing the organic compounds, or shorthand formula. Okay, so here should be a hydrogen and here should be a hydrogen. So if I would like to find out whether this is a cis or a trans isomer, I will draw a line like this that is cutting the double bond into two parts, and I have here the right carbon and here is the left carbon. On the right carbon, I have here a methyl group and here is a hydrogen. Of course, the methyl group is of the high priority. On the other side, I have this tertiary butyl group and a hydrogen group. Of course, the tertiary butyl is of a higher molecular weight, so it's the higher priority. So now we have the two higher priorities group at the same side of the double bond, so this is a cis isomer or Z. Okay? Another example, it had the same name, but if I would like to apply the cis-trans rule so that I find out whether it's cis or trans or Z or E, so I just cut the double bond into two parts, and I have here to draw the hydrogen, so the compound would be more clearer. I have here this carbon, which is the right carbon, and another carbon, the second carbon, which is the left carbon. On the right carbon, I have a methyl group and a hydrogen. Of course, the methyl is the high priority group, and on the left carbon, I have the tertiary butyl group and the hydrogen. Of course, the tertiary butyl is the higher priority group. Now, I should find out whether the two higher priority groups are at the same side of the double bond or at the opposite side. So they are at opposite sides. One, this higher priority group, which is the tertiary butyl, is above the double bond, while the other one is below the double bond. Okay, so this is a trans or E isomer. Okay. Okay, so now we have to keep in mind usually this priority rule to find out the cis and trans isomers or E and Z. Actually, this priority rule is attributed to the scientist Carl Ingold, who put this priority rule for the common atoms. And as you can see, the higher the atomic weight of the atom, the higher the priority it has. Okay. Thank you, and I hope if you have any questions, just put it in the comments. If you have a compound that you would like to put a name or understand how we can name it, please put it in the comments and I will respond as soon as I can. Thank you.